Hello, everybody. Welcome to this session in the Python for Finance online bootcamp. I think we now have a pretty broad, if not deep, but still a broad basis in Python for Finance already, having covered very important idioms and approaches with pure Python as well as with NumPy. So NumPy used to be the package that has drawn many people in finance to Python, to the Python ecosystem. And these days it is, I think, primarily Pandas because it's so strong with regards to the processing of data. It's pretty efficient. It's relatively easy to learn and to master. Maybe mastering, of course, as usual, takes a little longer, but it's easy to get high value for, let's say, little input, even from the beginning. And we can use Pandas in combination with NumPy, in combination with certain idioms that we have learned before, pretty efficiently and effectively in the financial domain. And in that sense, we are going to build on top of that what we have done so far, and we'll primarily be focusing on Pandas today, on the Pandas package. Before I get started, so in our recent email, I said, well, investing and getting started with our certificate program, which is in contrast to this bootcamp, not free, is an investment that many shy away and say, well, I'm not really sure whether I get enough value out of that. I see that, right? I see that as an investment, and like investing in a stock. The future is uncertain. We have done our simulation, right? Therefore, it's difficult to tell when you now invest, let's say, $100 in a certain stock, in a tech stock, maybe what the payoff will be in 1 year's time, 2 years' time, 3 years' time, right? The same holds true, of course, when you invest in education. I think it's still one of the best investments that you can do. And now that you have gained a little bit of an exposure to what we do in the program, how this is all organized, how my approach might fit your requirements with regard to learning Python for Finance, we have decided to go with a late entry offer for our certificate program for those who haven't signed up yet, which is valid for the next 48 hours. And it is at the super early bird rate. So if you have missed our recent super early bird options, so for the next 48 hours, if you want to get started with us with the next cohort, the May cohort, from Monday, or if you say you want to self-study, you have now the chance to get on board again at our super early bird rate. If you have any questions on top of that, I don't want to go into further details here with regard to the commercials in this bootcamp, but this is the message. Go to our page here, https://certificate.tpq.io, and over the weekend, if you like, until we get started next week, you have the chance to still sign up at the discounted rate. Yeah, with regard to our topics, I said it already, Python is of course what provides the overall framework. NumPy is a pretty powerful package with the ND array object and so many other functions that you get there in the form of universal functions, in the form of let's say linear algebra, ordinarily squares, regression is one example, functions there, and many more. So we have really just scratched the surface, but also other convenience functions which we have learned about, for example, to import data, CSV data, in an efficient way, and having that then available as what is called a structured and the array object, right? So it's still, again, on the surface, but if you by now don't know the benefits, it's not easy to find even more. I mean, just think of the speed advantages that we have seen, like orders of magnitude faster with regard to typical mathematical and financial calculations. Right, so that's of course something that it's not negligible, 2 orders of magnitude, a factor of 100 and plus. I think it should become one of your major go-to tools if you do anything with Python ecosystem in finance. And now I would say probably similar things about Pandas, but the focus, the twist, usually slightly different. Although we, if you like, inherit many of the benefits like vectorized operations, pretty fast calculations in the Pandas ecosystem as well, because to a large extent Pandas is built on top of NumPy, and therefore what we have learned to love will be available basically throughout, with a few differences, right, and a few additions as well. So it's not only that we have the core and the array object and the tiny twists around that. No, it's much more that comes on top of that, right? So with regard to the optional topics, so if we look, we have done a little bit of statistics. Today I want to dive also in the machine learning part a little bit. Again, financial applications, but it will be more on the trading side, and we will also cover a bit of vectorized backtesting. And given recent comments, I will also towards the end show how to deal with streaming data instead of historical data, where you have more or less a process importing once, processing once, and then do whatever you want to do. With regard to real-time streaming data, you need to be the code needs to be, and you maybe yourself as well, need to be present and active all the time. So that's a kind of a difference, and it's so important, obviously, in the trading arena when you want to get started with algorithmic trading. For example, of course, you need to digest the data that's coming in, you need to process it, you need to come up with the signals, you need to place trades, etc. And that's what I want to cover towards the end of today's session. But first things first, getting started with Pandas. So going to one of my Jupyter lab installation now, I'm simply using my local one, but you've seen setting up an infrastructure within a Docker container, setting up an infrastructure on a remote cloud server. It's not that involved with the packages and the package managers that we have available these days, like Mini Conda, which comes with Conda. This is usually a pretty efficient affair. So Python for Finance, online bootcamp here, clean slate, and that's now for the Pandas package, right? The Pandas package. And I'm using it since quite a while. I can recall that the first talk that I've given using Pandas was back in 2011 at the EuroPython conference in Florence. Back then it was pretty nascent, but what Wes McKinney, the original author, the main author, has done was already that beneficial that I was quite happy. Now we have an ecosystem. Last time I checked, the documentation in PDF form was close to 2,000 pages. So that's I think it's I would like to say it's massive. It's simply a massive package, can do a lot, and not only in and of itself, but it does a great job in wrapping other packages such as NumPy that we're saying, or Matplotlib for plotting, or many other packages that are in the ecosystem into one coherent API setup, if you like. But before, let me try, and I think it's not, well, on my machine it should be there, right? Import pandas as PD. It's not there, so happy so that I can install it. But I must confess, I don't know in which environment on my local machine I'm currently, but this is not a big deal, right? Percentage conda install pandas, and I put here the -y flag, then going to execute it. I can already now go and comment this out. See here, for example, num expression is one of the packages that is nicely wrapped. That's, for example, a package which allows you to evaluate numerical expressions like those that we have encountered with NumPy even faster. So that's one of the examples in this regard. Right, once you have it installed, we are usually pretty quick in importing it. Only for the first time, it takes a little while in the back end to get everything sorted. From the second time onwards, it doesn't take a couple of seconds. It's rather a bunch of milliseconds to import it. So now you might wonder, what is the big deal with what are called data frame objects? There are two main objects, the series object and the data frame object. I want to focus on the data frame object because from my point of view, the series object is a specialization of a data frame object. We could also think of the data frame object being a generalization of the series object, but I'd rather like to think the other way around, because the data frame objects are at the core. So when I, on top of that, import NumPy as well as NP, I will be able to generate a NP range, let's say a pretty simple ND array object. You know, this gives us numbers from 0 to 14, so 15 is excluded here. And I want to immediately get started with reshaped version 5 and 3, so pretty small, but nevertheless we have it here already in 2 dimensions. So instead of a vector, we now have a matrix from a mathematical point of view, right? So this would be our array object with a few numbers. So primarily data frame objects are used for what is called tabular data, and here you see an example for tabular data. A matrix, right? You have 2 dimensions, you have columns and you have rows. That's what is usually called tabular data. But with a table, you probably have something like column headers and maybe row indices. You can also think in this context of a Excel spreadsheet. The spreadsheet has like A, B, C, D, E, and 1, 2, 3, 4, 5 as the column, as the row numbers, right? That's kind of like a close analogy. But as you will see, we will be able to deal with pretty large data sets in a very efficient way that would never be possible with an Excel spreadsheet, even if some people out there will tell you so. Of course, you can, for example, now that I'm speaking about spreadsheets and Excel, you can combine the analytical power of Python with Excel, but then usually the heavy workload is taken over by Python. But speaking of a data frame object, usually in the documentation you find df as the variable name here. You can construct out of a data set here in the form of an ND array object. You can construct what is called a data frame. Right? You see here, by default, we get already after this transformation or instantiation, we get column headers and row index values, row indices. So type of the app now is Pandas data frame. And that's really at the core. And what I was saying before, that many of the nice things that we have loved to learn with NumPy as compared to Python, and I'm not yet speaking of speed, but I'm speaking of convenience and vectorized operations, they carry over. So when I evaluate 2 times df, I get element-wise multiplication here, scalar multiplication, right here. That's a vectorized operation, like with NumPy, scalar multiplication. Right. And things like df plus df, if we like, they work similarly, or df to the power of 2, like square root. I mean, you might have guessed it. We have here the same mathematical calculation capabilities, and even if you like df to the power of df, the fancy or more fancy example with the large numbers, this works as before. And throughout, you see, we get here our column headers and the row indices. So you also see that JupyterLab by default, Pandas in combination with JupyterLab, gives you here a HTML table with Hoover effects and gray backgrounds for every second row. This is contrary to what we see usually here for the ND array object, where we just have ASCII characters and no fancy highlighting, Hoover effects or whatnot. Right? So if you want to suppress that, right, you can do something like print. And now I choose another example, NP square root, something that we had, and I calculate the square root of the elements. And you see when I use print, it transforms the fancy or more fancy HTML output into regular ASCII output. Sometimes this might be a little bit nicer. You might prefer that even. That's often more compact. There are pros and cons with regard to fixed width characters, obviously. So that's one message from the calculation capabilities, the syntax approach with regard to vectorization. We are still on the same side. We just have, and so far I haven't made any use of it. We have, as it seems, just column headers in the form of numbers and column and row indices in the form as well of numbers by default. Right? When I have a look at this here via the attributes df dot, and when I then use the tab key, this takes a little while because there are so many attributes and methods attached, so that this is taking a bit for all of them to be collected. When I look up now here columns, right, you see that we have this as a range index starting at 0, stop at 3, excluded as usual, step size 1, and the index here, index, it's basically the same in terms of type, range index. But, and now comes the point, we can do better. While, for example, with regard to Excel spreadsheets, we will always have like the ABCs and the 1, 2, 3s. In this context here, we can define them. So df columns, I can override the range index values here by, for example, using list of ABC, let's say. Afterwards, I end up with a table where we see the column headers ABC. This would now be in line, let's say, with the Excel spreadsheet, although the numbering starts with 1 there. Right? So ABC changed from 0, 1, 2. Same holds true, you might have guessed it, with regard to the index. Right? List, and now I can go with A, B, C, D, E. I need 5 here. So that afterwards I have now capital letters for the column headers, and I have lowercase letters for the row indices. So far, so good. Question now is, can we do something with it? You might have guessed that one as well. Yes, we can. Similar to our structured array, where I was able to access a column which contained Apple stock prices or euro US dollar quotes, I could use what was called names there. And here we speak of the labels. We can use labels here as well. So df of A gives me the first column. Right? Now you might wonder whether I can do df of lowercase a. You see, it takes already a little while here. No, there it says it's a key error. So the bracket approach here is reserved for the column header so that I can access any column, but this simply does not work, right? It says a key error because it's looking in the columns and the lowercase a is simply not found there. Big surprise, right? So this is not simply not there, but we can try maybe something else. Let's say I go with df of 0, for example. Yeah, 0 does work because with NumPy in the array object or with list objects, we started our index endeavors with 0, right? We would have expected maybe we get simply the first element, whatever the first element is, but here the same holds true. It simply doesn't find as a column header a 0. Before we would have been more lucky, but speaking of indexing, we can do, for example, the following. Lock, we can use lock. This is for the locator, right? The locator. And now let me try it here. This now works. So LOC, locator, and here it counts or what you need to obey to is index first. So with lock, it looks first for the index. And then we get here the row values, ABC 0, 1, 2. df lock, just so that we have tried it. This time around, this does not work. But what will work is when I, for example, say, give me all the rows for column A. So colon means all, and then suddenly we are lucky and get the same effect as here for df in brackets A. So I would say quite optimistic when I was saying, well, with regard to indexing and accessing data, it's more or less the same. You see here, at least from a syntax point of view, with a bracket approach, it works a little bit different. But I would say this is not a big surprise because we now have simply a different object where we have the column headers and the row indices. When we want to save our story about the indexing, right? About the indexing, we can use something else, namely iloc. This is the index locator. And now let me try with 0. And in that case, we get the first row. We get with 1 the second row. This is now the second index. And we get the third one, right? So all of this works, right? And we can combine this as well. Now here, when we say, for example, give me row 2 to row 4, so this would be 2 and 3, right? So this is now a slice, and then on top of that, I can say, for example, 1 to the end, right? And now you see we have the final 2 columns. Many options. You might think, well, it's just a 2-dimensional object, but we have so many different options of accessing the data. The one is via the names. I should be careful here with the language. The labels here, right? The names of the columns and the names, which means here the index values for the rows. That's one way, right? Via the brackets and via locator. And the other one is, as we are used to with the in the array object, let's say, via the numbers, the index values or position values, if you like, via iloc. So these are the 2 basic ways of accessing data. In many applications, this might not be that relevant, but it gives you a large degree of flexibility with regard to what you can do with data, how you can access it, and maybe the implementation of more sophisticated algorithm is simplified by that. Of course, this is giving you the flexibility. The programmers of such a package, they might not even remotely anticipate what you want to do, but they give you powerful tools at hand so that you can accomplish basically every goal, and hopefully in a pretty efficient manner. So these were here not methods, these are indexes like .lock, and whenever you see brackets, this is about indexing. But we have learned with regards to the ND array objects that we have something like methods for calculations, like df sum. Let me try df sum here. Oh, this works. But when I have my A object, right, the array object, and I say A sum, this by default gives me the sum over all the elements in the ND array object, right? Here, sum of all elements by default. You know, we have seen that we can use axis 0, axis 1, and here we get the sum of the elements per column. And this is something that I want to emphasize at this point, that we have in the Pandas world something that is called column first. So by default, we have column first, while in the NumPy and the array world, we typically have the default of, at least for aggregation operations, that the calculations are done over the whole data set, no matter what the shape, no matter what the number of dimensions is. Maybe other things, df mean, have a look here, the same for the average. This works the same, right? We get the columns, but we can force to do it differently. That I say, for example, df mean axis 0. This is the default, right? Default by column. And df mean axis 1. This is now row-wise. We get here the average value for every single row. So this works here as well, the axis approach. If you want to get the mean value for everything, you simply do it twice here, right? So you chain it and say mean over the column and then the mean over the column value. So you end up with 7, which would be a mean, right? So here we need to do it twice to arrive at the same result, right? So far, I would say many things that we would like to have are the same as with NumPy and the array object. Some elements, some default behaviors are different, slightly different, or you might feel like a major difference. But I think there is good reason behind default behavior in that context, because I was saying before, Pandas is not about tiny tweaks and twists around any array object. It has its own purpose, and that's primarily, I don't know if the maintainers of the package would agree, as a group, but primarily for the crunching, working, processing tabular data. These days you can do much more, but still, for me, for many others, that probably is the core use case in this context. So maybe some speed comparisons here as well, so that we have also here a look on that. We have had things, let me get started here with n. Maybe we go with 10 million data points, right? 10 million data points, and I create a random number set, random numbers of, let me do it properly with the current wave from NumPy, a random import default random number generator. Then RNG is the default one without setting a seed. Reproducibility is probably not here. So in order, so let's go with the standard normally distributed ones, standard normal, so that we know roughly the mean and the standard deviation. Now we go with the n value, and I do a reshape, reshape n over 10 and 10, so that we get now 1 million rows and 10 columns. This needs to be an integer. So it was complaining that here, whenever I do a division, the result will be a floating point number, and I cannot use a floating point number here to do the reshape. Therefore, I need to transform this to an integer. Okay. Now I can create my data frame, PD data frame, with the random numbers, and you see we have 10 columns. I'm now not concerned with the labels, so the column headers or the index values, that's fine. So 0, 1, 2, 3 to 9 here, and from 0 to 999,099. Right? And there are certain convenience functions like head that I can use to show the first 5 rows. df tail shows me the final 5 rows here. And there are many more functions. I can for example, use info. That's a good one. You see, info gives you metadata about the data. So it's not the data itself, nor statistics, just like accounting. But we have like a million values here for the different columns, etc. pp. You also see the memory usage here at 76.3. It's not a tiny data set, but it's also neither a large data set. For df describe, this is now more on the statistical side. df describe, you see it took a little bit to do the calculation. We get the mean values, they should be close to 0, right? The standard deviation, minimum 25, 50, 75 percentile, and the maximum values here. So this is pretty wide. Maybe I do a print, for example, and a rounding to 3 digits. Why doesn't it round to 3 digits? What is that? Oh, I did it after the print parentheses here, right? But with the first value already, we have that large number. I think this is a bit more compact. So you see many convenience functions. Again, this is something we cannot go through in an exhaustive way, but we now have our large data set, right? And what we do when we want to do calculations, like with the random numbers themselves, this is the ND array object, right? And I can, for the ND array object, for example, just to be sure, we have the shape of 1,010,000. So we would go here and do, for example, Rn, time Rn, the sum over axis 0, and we get 10 sums here, 41 milliseconds. You know, with time it, we are getting much more reliable estimates for the time used indeed, and not something with overhead and sending the message. So instead of 41, you see 9.12 milliseconds. So we know by default we have column first, meaning here the axis parameter is not needed. Time df sum, so it gives me the sum per column by default 62. Again, we should rather do the time it approach. This also suppresses the output, but this is not a big deal. And you see here, it is fast. I would say faster than something similar in pure Python, but the mathematical capabilities here of a pure NumPy are often more performant. That's the reason I don't want to go into details here, that even if you are working primarily with Dataframe objects, it might often be sensible to transform for numerical operations to get a ND array object out of the Dataframe object, right? So this might often be sensible. You might have seen this, or you might need this in the future. Maybe if you want to save here, it's like 2/3 of the time executed. Let me do maybe one more example with regard to the universal functions. What we've had, NP square root over all of the values, right? So this gives us a invalid. Oh, for the square root, we have negative values, so this doesn't really make sense. We don't have an app, so let me go here with n. Yeah, maybe it's not a good example. Well, we can do it. NP apps, the absolute value. You see, it provided me with a warning. It didn't break. That sense throwing an error, right? But obviously, working with regular numbers and not complex numbers for the negative values, we don't have the square root defined. So that's here the output for the NumPy and the array object. 27, still faster as before. And when I do something like this now with a df, the data frame, not needing the output here, you see there the difference is not that much, because this is element wise over the whole object. Before we have seen a major difference, here the difference is not that pronounced. But overall, I would say df data frame objects here are also pretty fast in terms of the numerical operations that you can implement on them, right? So that's a good message, I would say. We have seen the capabilities also with regard to the calculation, etc., and the speed is also preserved. So overall, we are getting something to what we have had and preserve the good stuff. So I now want to showcase, because this is from a, I would say, convenience point of view, visualization of data, where Pandas is also doing a great job. Right? And before I do the visualization itself, I want to introduce here datetime indices. So PD, there is now a function which is called date range. So when you look it up here, what you can do there, these are the important parameters: start, end, periods, frequency, time zone, normalize, etc. So returns a fixed frequency date time index. I think the name speaks for itself. We have been dealing with datetime objects, date information, maybe time information or combination already. It was one of the last things that we did in the previous session, where we transformed the strings representing dates into datetime objects. Here in the world of Pandas, we have something similar to the datetime objects, and they are called timestamps. There is a close relationship, so I can say they are maybe brothers, sisters, siblings, or at least cousins, right? With, I would say, the slight benefit of the convenience here for the Pandas timestamp. So when I want to create an index, and one of the benefits here is the convenience function of date range, and a few more that we have, we can get started, for example, with 2024, let's say 1-1. That will be the start point. Now I need to decide, do I choose end or periods or frequency? I cannot choose them all. I now go with the periods, and I say, for example, 200 or 512. 252, it's 504. So 2 years, 2 trading years, and the frequency, I could go with daily with D, but it has something like B for business daily, which gives me only the weekdays. So when I execute this and have a look at the object, you see that this is again another class, another beast, as I like to say, called the datetime index. It starts at the 1st of January 2024. And goes here, as you can see, right, day by day, but it's only weekdays, so it doesn't take into account any holidays, bank holidays or whatever. But you see here it's 4, 5, and then it jumps to 8. So that's the weekend. The 6th and the 7th is a weekend, and then 5 more, and so forth. Right? The length is 504, and you see roughly we end here at the end of 2025. I could also go with other frequencies like weekly, for example. This brings me to 2033. But let's say we are dealing with end of day data here, or let me just show D. D is now every calendar day, so with including the weekends, with the weekends as well. But I go here with a business business world, right? So even if the 1st of January, usually there's no business going on apart from the crypto world, maybe. So this would be a time index, a date time index. Right? The next thing that I want to do is I want to define my columns, and the columns here, I don't want to come up with fancy names here, right? I can simply do as I did before, list of A, B, C, D, E, for example. Then I have like 5 columns. And I want to go now with 5 columns, and this should be the index. This should be the index word, right? So having these available, I now want to draw random numbers again, like I did before, RNG, standard normally distributed ones with the following shape. I have the length of the index here, and then the length of the columns, so that we have the appropriate number of the random numbers. So I needed to put this into parentheses. See here, right? I need to pass the shape as a tuple in this context. Now the construction of my data frame looks as follows: PD data frame. I pass in my random numbers. I will change this a little bit afterwards, the random numbers, and in the next step, the columns here, and then the index is set to the index. So before, I only use that part, right? But I can, during the instantiation, also specify the column headers as well as the index values, right? When I now have a look at it, A, B, C, D, E, and the 1st of January 2024, 2nd, and so forth. So, and in between there are the values. What I now want to do is I want to let me change one thing here. When I go here for 0, I want to set the first values for my random numbers. I want to set to 0, so I'm overriding this so that we have an equal starting point, right? And then I go and calculate here the cumulative sum along axis 0. So now we start here at 0, and then we do the cumulative sum until we end at a certain point. We don't know here, you see, by chance this is positive, this is negative, etc. And if we fancy, we could also do something like plus 100, so that we start at 100 and then we have a stock evolution. So what I want to do here is kind of like simulating some stock prices. You might have guessed it, given what we have done in the NumPy context. And now the time has come to do the visualization, because this whole section here is called visualization of data, of the data. What we would usually do, what we have done so far, is let me do the import. So pylab import PLT, then we do something like PLT style use and set it to C born -v 0_8, right? And do our config inline backend bigger format SVG. So that's my default configuration for plotting here Jupyter Lab. Let's just give it a try. PLT plot df. Let's see what happens. So with the ND array object, we were able to basically do this, right? And here you see, out of the box, without telling it anything about orientation or whatnot, we get now our 5 random walks that we have simulated, we get visualized in a nice fashion. Of course, the style here is as I have chosen it before, right? I can suppress the output, as we know, with a semicolon, but overall, PLT plot df, wonderful. Out of the box, we get a nice chart. Matplotlib understands the date time information in the index. What we don't have here is a legend, right? We don't know what, well, we have column headers, but we cannot spot the column headers yet here. So this might be something, right? But there is, this is not, let's say, the default approach that you would do. It works. I just want to send this message. But what you would do, and this is now where the power of Pandas wrapping comes into play, df plot, right, works as well. So let me put the colon. So when I write df plot as a method, it more or less looks the same. The behavior is slightly different. You see the formatting here on the x-axis is different. Here it was simply going quarter by quarter. Here I would prefer that here, Jan 2024, April, July, October, etc. And what we also get out of the box here is the legend, A, B, C, D, E, right? And simply by using one call here, df plot, we are in the game and we can visualize our simulated stock prices or whatever this should stand for here in a very efficient manner. Of course, the configuration here, this wouldn't be necessary, right? By default, it would simply go with the default matplotlib, but here we can also do quite a bit more. Right? We can, when I copy this here, so copy, and let's have a look at the documentation, the doc string. What is it? Why doesn't it show me? What is the issue here with the plot method? Well, that's strange. That's kind of strange. Why it's not showing that? Here it works. I don't know why plot question mark didn't work. Maybe some issue. I don't know. But help df plot works. You see, I passed the data x, y. Then we have different kinds of plots that we can choose. And when you scroll down, I don't want to go into the single parameters here. Many more, like legend. We can turn on legend, off. By default, it is on. Style for the single lines, X label, Y label. I just want to afterwards use a few of them. And down, you see not all the capabilities of matplotlib. This would be impossible, but I would say for the 80–90% of the typical use cases, the capabilities of matplotlib are wrapped here into one single method. And to scratch a little bit more the surface, df plot, here we can say X label, for example, date, for example. So let's see. So it now puts here the date. Then, for example, Y label. So adding one after the other, Y label might be prices. Of course, random ones, simulated ones. We can put a title in here. Simulated stock prices, just as an example, right? And what I often like to change is CMAP, the color map, cool, warm, and we get a completely different color map here, from cool, which means dark blue, to warm, which means dark red, and a few in between. The gray one is not that good to spot, but I like that in particular when you have many more than 5, right? So, and quite a few more options where you don't need to be an expert with matplotlib. It's simply enough here to have a look at the options and the parameters that the plot method gives you and to make use of them. So out of the box for many standard visualizations, that's already a pretty good thing. Maybe just as one more, we have had a case where we did calculations with regard to the log returns. Let me calculate the log returns here. This might be good if we put visualization, log returns with regard to the calculation. We have done this twice, and the visualization in the form of the histogram. So the log returns here can be calculated as follows: np log numpy, vectorized operations are possible. Now I take df and divide it by df shifted by 1 day. This is, you should compare this for your own benefit with the approach used with NumPy. And after this little calculation, we have a complete data frame which now contains the log returns. The first row is empty because we don't have a reference value for the first day here in the data set, but then we get here the daily log returns, trading daily log returns. So maybe also with head, leaving the first one. And the second part here, visualization, LR plot. We have seen this kind can be chosen to be histogram. And I get a histogram for all the 5 of them, but one on top of the other. Here it says frequency. Here we get the 5 of them. And let me do the following: subplots true. So this gives me now 5 histograms. Let me go with the bins 50. Now we have 50 bins here. Yeah, you see, I could now go on and on. And so there are many more types of plots and configuration capabilities, messages. Pandas powerful, might say tabular data, fine, but I hope you see here the benefits in terms of efficiency as well, in terms of wrapping the capabilities of other packages into a single coherent API. So speaking of coherent, I don't want to be like the one who's only on the positive side. Over the past, there have been, I would say, a few issues with API consistency and what the team decided to change, where old code was breaking. But I feel that over the last 18, 24 months, at least what I'm using, what we are using with regard to Pandas has been pretty stable. This hasn't been the case in the past, but now it feels like a mature environment where you not need to every 6 months change parameters, arguments, method calls, whatever, in a significant manner, right? Yeah, that's maybe a little look at the basic capabilities of Pandas with the data frame, tabular data, column headers, here the time index, for example. And yeah, that's, I think, a good starting point, which allows us to turn our attention to the data case, to our data set that we've imported twice. I now want to repeat this with Pandas, and trust me, this will be a pretty efficient affair. So I'm going to push this to the gist so that you have the latest version in the gist of what I've been doing. I need, of course, to reload this. 5 Bootcamp. So Pandas package now all here in the gist. Wonderful, right? So the next Jupyter Notebook should now be dedicated to the importing and working with the data set. shut down the kernel here, introduce a few cells, financial data. So let me do my regular imports, import numpy s and p, import pandas spd from pylab, import plt style use. I hate typing this seaborn thing there, honestly. 08 and config inline again, bigger format SVG. Good to go with our data set, the URL, HTTPS, certificate, dpq.io. Think of what I said in the beginning, visit that page and have a look. And yeah, it was the findata.csv. This was one stroke too early. Data set. With the pure Python approach, we retrieved the text file and then we did several splits until we ended up with nested list objects. Then we transformed the strings into floating point numbers and were able to do several calculations and in the end also some visualization. With NumPy, basically similar approach, a little bit of tweaking of the gen from text function, few parameters were needed, for example, names true and dtype none, and like this. Now let's have a look at how this works. We have here a convenience function, pd read CSV. Now I pass simply the URL, and when I execute this, you see I get already a data frame. You know, whenever we get this this output here with a hoovering effect and the nicely formatted HTML table, right? We get already that data frame. So this is pretty large. Maybe I do a print here so that we get it in a more concise manner, right? So, but just like PD read CSV URL, and we are, I would say, 90–95% there. We have the data. We see a couple of not the number values. We have here the date column, which by default, as you can see, is interpreted as a regular column. So we need to use one parameter in combination with a flag that we need to set in order to be on the safe side. So having said that, let me repeat the exercise. PD read CSV URL index column 0. So when I say index column 0, I get the first column in the data set now presented as my index values, right? So that's the data. When I now have a look, data info, I have the following numbers of values. Here are the column headers, right? Apple, Microsoft, Intel, Amazon, etc. I get the index entry. So this is the only thing that remains here. We need to put or set one flag, namely the one parse dates to true, in order to end up with a datetime index. Now have a look here, it says still index. When I now have a look at it, it says datetime index. And this is what we would like to have when we work with time series. Like what we did in the previous notebook, which we generated via the date range function. We generated the datetime index object and used this as the index for the data frame. Right? So that's now our state. We have the data basically with a single line of code, no processing required whatsoever. We have, or after processing, pre-processing, before we can do visualization or whatnot, we are good to go. And speaking of visualization, we have done so, for example, with Apple. So here, Apple, I access now the column, calling the plot method, and with a single method call on that column, I get the plot of the Apple stock price process over the 10 years. As simple as that. 2 lines of code, and I'm here with a plot of the Apple stock price. I would say it can be hardly any more efficient, and trust me, there is quite a bit more that it can do with that function. When you are faced with, let's say, non-standard formats, where you say, well, it's a semicolon instead of a comma, or whatever jumps to mind here with regard to the potential look of CSV files, the read CSV function is pretty powerful. And you can also read not only from comma separated value files, you can read from Excel spreadsheets, from SQL databases, from Parquet databases, and quite a few more, even from clipboards. When you go to a web page and you copy a table, for example, then you can read clipboard, for example, and it will get the information from an HTML table into a Pandas data frame. Pretty convenient and powerful, right? So now what I want to do, I promised this, I want to do a little bit of machine learning, right? And if you have never done anything with regard to supervised learning, what I want to apply now, it is maybe a little bit difficult, but at least it will whet your appetite maybe to try to implement such approaches to predict financial prices, right? So here, market prediction with machine learning. We have data here, and the idea is that we have the data that we can use to learn maybe about patterns, right? So that we can, given certain patterns that we observe in the markets, can predict at least the next day's direction of the move, right? Whether the market goes up or down. If we would be able to predict for, let's say, the S&P 500 with an accuracy of 70%, which direction the market moves, you would become billionaires in a very short period of time. So therefore, this is, if you like, one of the holy grails, if not the holy grail in finance. So what I want to do here is based on what is called lagged data. So first I pick, let me define a symbol. I go with the euro US dollar symbol that we have in there, and I pick one of the columns, PD data frame. I pick one of the columns of my, how did I call this, data? Yeah, I call this raw, right? Data, maybe I call this raw here as well. So raw, because this is not the data that we are going to work with. This is rather the data that we have imported and from which we will now get our data that we are going to use and that we are going to work with. So I'm re-executing the code. Now everything runs with raw. Maybe you have other preference with regard to the naming. And here, now I want to call this data and pick out the symbol as a data frame. So symbol is not defined yet, as a data frame. So data is just now the euro US dollar quotes over time. So I'm going to add a new column, something that we haven't done actively. You have seen that I can access column via the brackets, right? Access column via the brackets. But now I'm going to define a new column, namely for the log returns here. I've done a calculation like this in the previous notebook, NP log. I take data over data shifted by 1 day, right? And I end up now with a second column, euro US dollar and R. So this is that value divided by that one, and then the logarithm. This is that value divided by that one and the logarithm, right? So this is our, how should I say, the initial data set. We have prices and we have returns. So the whole approach now here, data pre-processing. So before we get started with any machine learning, you might have heard this, the data pre-processing often might take even more time, sometimes much more time than the application of algorithms. What I want to use in the supervised learning context, again, many of you might have had experience or have experience already, maybe a ton of experience with supervised learning methods. We will work with features and try to learn about the relationship between the features and the labels, right? So the label what we are interested in will be as follows. I define here the direction of the market now as the sign of the market return. So maybe let me put this up here. This makes sense. So now we have a +1 for a positive return and the -1 for a negative return. I think this should be clear, right? +1 stands for an upwards movement and the -1 stands for a downwards movement. The market goes up, the market goes down. Right? This is what I would like to predict. Based on what? Yeah, based on historical lagged returns. Right? And now I do the lagging. So lags, I set the lags to 5. Then I define my columns first as an empty list object. And now the lagging happens for lag in range 1 to lags +1. Right? I now define my column name as an F string, lag underscore lag. That's the variable name now. And data with the column name just defined on the fly, I do data R, the return, and I shift it by lag. So by 1 day, by 2 days, by 3 days. And afterwards, I append the column name. So this was maybe a bit fast, but when you see the data, I guess you will get at least the intuition. Speaking of the data head, let's go with the first 8, for example. So this is how my data frame now looks like. Daytime index, clear. Prices, clear. Log returns, I guess, also clear. The direction is simply the sign +1 -1 of the return. And now we have the lags from 1 to 5. So 5 lags, here it is defined, 5 lags. And I push the R column down for lag 1 by 1 index value, then 2 index values, 3, 4, 5. From this point on here, we have 5 lags. The data set is full, and this is the next day's movement. So we want to look at the historical returns and try to learn, based on machine learning, what the next day's directional movement is. So for here, so we have thousands of examples with regard to historical returns and the next day's movement, right? And the idea now is, in supervised learning, use the features, try to learn from the features in combination with the labels that we give to the algorithm, the relationship between the features and next day's movement. As simple as that, right? Now that we have the data, the application should be, I think, pretty straightforward. Oh, there were kind of like questions in between. There's a question with regard to how to access the different functions. Yeah, you, for example, with the data object, you put a dot behind it and then press the tab key. Upper left-hand corner of the keyboard in general. right? Here, press the tab key, and then you get apps, add, etc. pp, right? Oh, there's somebody who was already explaining it. Thanks so much. I'm always happy when people following along help each other. Wonderful. But here I'm showing it again, right? So put an object, then dot plus tab key, or let's say you have something in mind, put a C, for example, or a CO, and then you get like a selection given your first characters here. So it narrows down the field of possible options, right? So the data is there. Why is calls a list? Yeah. Why not? What else should it be? Give me some some input here. I can tell you, of course, immediately why it is a list. It's not a data frame. Calls is just, you see here, I collect the column names. Calls, let me show you that. Calls is only a collection of the column headers here that are representing the features. I will use this to access exactly these 5 columns. That's the major reason why I'm collecting just the names. It's not a data collection, it's just a collection of the column headers. Right? So before I proceed, I do like a pretty brute force operation. I do drop NA here and write in place true. Afterwards, when I have a look at the head of it, you see that I have dropped all the rows where there was at least a single, not a number value. After this operation, I'm ending up with the data frame, which is complete in terms of the data per row. All the rows that remain have only complete data points, right? So that's here now the state, so that we can get started working, right? Predict. So yeah. Okay, can complain. Prediction based on supervised learning classification. So to have a little bit of a guidance here. What I would like to use to get started with is from scikit-learn something, but I don't have scikit-learn installed here. So as I did before, I need to install scikit-learn. Scikit-learn -y, but I need to type install as well. Install scikit-learn. That's one of the comparable, from my point of view, comparable to matplotlib. For machine learning, that's the standard package, the default package in the Python ecosystem. It doesn't mean that's the only one. It doesn't mean that for certain purposes it's the best one, but it is like matplotlib, a standard package of the scientific or the data science stack. Right, and when I've imported this, right, I can, for example, from sklearn, doesn't do my completion, naive base import Gaussian naive base. So it's doing, I don't know why, with freshly installed packages, it takes a little while until the index, etc., is built in the background. Therefore, I needed to type it out, and my so much loved tab completion didn't work out of the box. That's a classification algorithm. That's supervised classification, it's called, right? So what do I do with it, with these algorithms? We have with scikit-learn, and in principle, for example, with TensorFlow Keras as well. We are not touching upon TensorFlow, but just to have it mentioned, we have in general a 3-step procedure. And the 3 steps are as follows. I set up a model, I instantiate a model. Here it is the Gaussian naive Bayes. That's a Gaussian classification algorithm. No need for any parameterization. That's the first step, right? It's model instantiation. The second step is the model fitting. Now the question was, what is calls? Why it's a list? Now for the first time I use it. Data, calls, I pass it in here, and data, this is now features and the labels, direction. The column is the labels column. That's the second step, model fitting. So it shows me here some stuff which is not really of interest at this stage. Basically, it just says Gaussian naive Bayes. Okay, well, yeah, that's what we get started with. And the third step now is model predict, and I pass in only the calls here, the column names. That's the third step, label prediction. So we now want to predict from what the algorithm has learned the labels, right? So this gives us an output of +1s and -1s. That's what classification, binary classification is all about. Maybe I even write that one here, binary classification. It doesn't have to be binary, but the way we have structured the data, we end up here with a binary classification problem. So we only have 2 values to predict, up or down. Think other examples, think with regard to an exam, pass or not pass. Right? So that's a binary problem, right? Or rain or not raining, for example. And there are so many examples which are binary, obviously. Here we have now mark it up or mark it down. That's what we want to predict. And I want to store the predictions here in the P in my data frame object. Here I simply have executed this row, but now I want to collect it. I want to collect the predictions. Model predict data calls, so then I have it in a data frame and can do something with it, right? And I can also import it down here. Now I can think in terms of how good this prediction is. We know when we toss a coin and do a prediction up front, usually we would come up with like a 50-50 chance. Or you go to the casino, playing roulette, betting on black or red, excluding the green 0, 50-50 chance. When we want to predict the markets, we want to be better than 50%, right? Tossing a coin would be usually already on the 50% level. We might want to achieve an accuracy of 60% or 55% or whatever. Therefore, I now import from sklearn. Now it works. Metrics, import accuracy ratio. Now it's again building the index, accuracy score. I always say accuracy ratio because that's the term that I prefer to use, the accuracy score. And with the accuracy score, I can now check how good the model is able to predict. This is the original data, D, and data P, this is the prediction data. And the prediction accuracy is slightly above 51%. So that's, yeah, at least better than 50%. No doubt about that. It's 1.1 percentage points better. But if this is good or not, this needs to be verified in a next step. And speaking of a next step, I now want to introduce briefly vector. Yeah, what is with this editor here? Vectorized, I'm typing too fast or too slow, I don't know. Vectorized backtesting, something that is at the core of, I would say, many algorithmic trading endeavors, what we teach intensively and comprehensively in the program. But the basic idea, the basic approach is kind of easy to implement. The major goal is to use the predictions and to judge the value of the predictions in economic terms, right? Meaning that being right or wrong, it's just one side of the coin. In the financial markets, you might have heard about this. It's important how large the movements are that you predict correctly. For example, if you predict correctly that a crash is happening next week and the market drops by 20%, that's something where you can make a ton of money, a ton of cash, right? If you predict tomorrow's movement, which might be 0.001%, you have done a correct prediction, but yeah, with such a small move, it will be difficult without high leverage to benefit from it. Therefore, vectorized backtesting puts the economic twist now into the game and goes beyond the statistics of the accuracy ratio. So what do we have? We have the log returns, we have the predictions, and I can now derive the following. I can derive S as the strategy returns in the following manner. I have the predictions, and now from a trader's point of view, I say when the algorithm predicts an upward movement, I go long, and when the algorithm predicts a downwards movement, I go short. Therefore, I go with the exact predictions and multiply the predictions by the market return. So this implicitly assumes a number of simplifying assumptions, like with regard to the collateral that would be needed for short positions, etc. But it is a first good indication. So giving us now the strategy returns. Strategy returns under simplifying assumptions, so that we don't forget about that. It's just a statistical analysis. It's not a fully economic analysis, or let me say it's like in between the purely statistical and the purely financial analysis, or the correct financial analysis. It's something in between. So what can we do now? I have as a benchmark investment, I can always say I go long the benchmark, right? So the benchmark here would be the symbol. When I plot this, as a long investor, I would lose money with a euro-US dollar here, right? As a short investor, I would make some money. Now the question is, when we predict up and down movements, can we benefit based on our strategy? And that's here R compared to S. And I now calculate the sum of the log returns, and we get negative values, makes sense, for the passive benchmark investment, and positive values. So this is simply, this is the sum of the log returns. This is not yet in real world numbers what we should focus on. We would need, and now you learn about a new method. I can use apply here and pass in the exponential function to come up now with the absolute cross return, so the cross return. This means that $1 invested in the euro-US dollar gives me 81 cents. I'm losing. $1 investment in the strategy here based on the predictions gives me 1.37. Right, and I can do this now also visually and over time, which is one of the key charts that you will see when you study more with us, that you will see. So I use here the cumulative sum, which gives me the performance over time, right, day by day. And usually I plot this and don't have a look at the table here. And you see that in this particular case, Passive benchmark investment, no surprise, we've seen this before visualized. With $1 invested, we would, or €1 invested in that particular case, euro US dollar, we would lose some 19 cents or 18 cents. With the prediction strategy of the machine learning based approach, we would gain over time here, right? So we would gain some 35, so what was the number? 37% here. Okay, yeah, thank you for providing additional input here and support for the question that we've had before. And yeah, you see the prediction based one, and there's so many simplifying assumptions, right? No transaction costs, no collateral for the short positions, etc. pp. So, but it is a starting point. You can make all of this always more realistic, more sophisticated, etc. But at least it is a machine learning based prediction approach based on binary classification, supervised learning with lagged returns data and binary directional data. And there are a ton of different options. If this is a topic of particular interest, we in the program do a lot of that stuff from many different angles. Or you have a look, for example, at my book, AI in Finance, which focuses on the approaches there as well, with deep neural networks, recurrent neural networks, convolutional neural networks, and quite a few more approaches, reinforcement learning, for example, that are applied to problems like this. Maybe just before we then do a brief break, maybe just one adjustment that I want to make. So here we have a very simple classification algorithm. No parameterization has been done. It's simply the model as it is. The major hyperparameter, if you like, that we have here is the number of lags that we use. So we have used 5 lags, but who says that 5 lags is a good number? Maybe using 6 lags or 7 lags might be better. So let me just do this one change there and re-executing the whole notebook, like 7, right, instead of 5, and I just like execute the whole notebook from scratch. Takes a bit, obviously, right? And we end up here just by changing it from 5 to 7 lags. The performance increases here from 37% to 153%. So, of course, what we are not doing here, right? Remark. So this is a very simplistic, illustrative example under simply by assumptions. It ignores aspects like transaction costs as one, right? And among other things, it implements an in-sample analysis only. So no train test split, for example. I could write a long list now, but I want to have this here as a remark. So later on, when somebody has a look at this, this is just for the sake of illustration with a focus on the Python side and the applicability. Right. So now that we are on the safe side, I could put this in red, but I hope that is good here when I have set it in bold letters. But at least we have done an application to a real financial time series based on a supervised machine learning algorithm, binary classification. We have predicted the market, and in sample, we have seen kind of promising results. Of course, we would need to check whether this approach and if so, how it applies to out of sample data, meaning how it generalizes, and need to add more realistic financial assumptions to the mix, etc. pp. But that's the starting point. But it's only a starting point as well, right? Yeah, having said that, with a word of caution, and this notebook now cleaned up, I can push it to the gist for your reference. I think it's now a pretty good point to have the 10-minute break, right? And yeah, with regard to the question, autocorrelation, yeah. Again, we have many issues that would need to be addressed in this context. This was a technical illustration and not, if you like, financial advice, or in any case, proper financial use case. It was just a use case here based on financial data, but you need to do quite a bit more in order to get to a, yeah, let's say, consistent approach in this context. Yeah, 10-minute break. See you back in 10 minutes, and then we turn our attention to streaming data, which is also so important in the trading world, right? See you back in 10 minutes. All right. As promised, we're now entering the world of real-time data, and I will not use any kind of real-world API, which might be available at certain points in time or not, for which you might need credentials or not. What I'm going to do, and this is what I like to do, and I think it's really instructive to learn how to deal with real-time data, is to develop and to implement a tick data server from scratch that we can then in turn use to retrieve the data as we would from an API in the real world, and then do something with the data, whatever the something is. So we can, for example, use Pandas to collect the data and do some more stuff. So far, our major tool has been Jupyter Lab. For the sake of efficiency, simplicity, and also for the sake of exposition, I'm going to use now the shell only. Probably if you have not that much experience with the approach that I'm now implementing, it will be difficult to follow along. So as I have pointed out in the introduction and things that I consider noteworthy, often it is better to lean back, to follow along, to get the gist of what is happening, and later on revisit it, and later on try to repeat it. Like, again, the analogy when your piano teacher is playing a wonderful piece, probably for the first time when you try to replicate it, it won't work that well, right? You need to exercise, you need to try, you need to fix, to tweak, and then from a certain point on, it will work. So that's just, again, my recommendation. So speaking of changing to the shell, I have an empty one here open, or an empty one, like a native one. And let me make sure that I see the Discord server with the question. So as usual, please all the questions on Discord. So it is the gist should be updated. I think that's that should now be the latest stage. I hope that I didn't forget it, but it doesn't hurt to simply repeat the exercise here and to update it. That's perfectly fine. And here now getting back again to my shot. So I increased this to have quite a bit of real estate, and I'm in my folder here where you've seen over the sessions of the bootcamp, we have grown the number of files that we have in there, primarily the Jupyter Notebook files, also the data file that we have downloaded from the remote server. I don't know if you've noticed, but we didn't need to access a local file. We simply could provide the URL, and Pandas was retrieving the data from the remote source. So I'm now going to use Vim for editing, and I implement a tick server file. So using Vim on the command line here provides a bit of efficiency for me. So this is a simple tick data server that we are going to implement. And to this end, I'm using a socket communication package which is called setmq with a wrapper pipe setmq. When we are dealing with real-time data, it is not like what we have been doing before, where we have a static data file on a server, for example. We retrieve the data and then do something with it. This is now like in real time, like the session we are currently holding live here, or when you have a telephone conversation. I've heard that these days still people talk on the phone, as compared to, let's say, exchanging emails, right? An email is asynchronous, communication. What we're doing here is synchronous, right? When I say something, you retrieve it. When it is recorded and later on uploaded on YouTube, for example, that's asynchronous. So next week, people can watch what we are doing currently here. With regard to the real-time data, we need to be able to communicate, to retrieve stuff in real time, like when we listen, let's say, to a conversation on the phone with somebody else. So therefore, I'm importing setmq here. The first object, the main object, is the context object that I'm going to instantiate. And from that, I create my socket object. So context socket here, and this will be the setmq publisher. That's communication pattern. The server is the publisher, like, let's say, the NASDAQ, where the prices are fixed and then communicated to those interested in the prices, trading in the market, doing risk management, and what else, right? Then I bind the socket to a certain port here, TCP. I go with 127.001.5555. That's tradition here with setmq. You know the default port for Jupyter Lab is 8888. Here it is 5555, and it's not Bing, it is bind here, right? Bind. So speaking in terms of the prices, I might get started. Let's simulate to make it specific, like Apple stock prices. Apple, right? And we might get started at 100. I want to have a tick data server which runs forever, and running something forever in programming language is usually while true. So this simply repeats what is coming in the while loop. So we have more or less extensively used the for loop, and here we have a while loop, which simply is based on a single condition, and the condition here is true, and while true is just a shortcut to say run this until it is broken, until there's a break command or there is a keyboard interrupt or whatever. So it would now be a little bit boring if we just have Apple with 100. So we want to have something like Apple where we do a random change. And we know how to deal with random numbers. This is here possible with the random package from Python, where I say add to the original value random Gauss 0 and 1, so something standard normally distributed, and I usually scale this by half. So I say normally this standard normally distributed is a little bit too much. I could also half, for example, here the standard deviation, but everybody has a feeling for standard normal, therefore I do it afterwards here. So this changes the Apple stock price in a random fashion. This approach is now in a real-time sense, in a simulation sense, online algorithmically. So we speak of offline algorithms and online algorithms, similar to what we have done today, where we did the simulation of the 5 stock price paths, have put this into the data frame and then visualized it. So this is actually pretty close. to that approach. Of course, here with a step-by-step approach, and before we did it in vectorized fashion. So when I do a print AAPL, just to check what is happening, I can now here, and these are my shortcuts in Vim. I hope they work, and I execute this program, and you see it's running fast, positive values, negative values. At least the code so far is working. I mean, at least something, right? This is going pretty fast. Therefore, like in the real world, I want to have also some randomness with regards to the timing. So import time, and I want to stop the execution here by a random amount times sleep. But first, maybe to illustrate the point, when I put the Python interpreter to sleep for 1, which stands here for 1 second, it would look as follows. So here we get every second now, we get an updated value. And the update happens in random fashion. Right? So this is not how it works in reality. In reality, the price is not known in advance, or we can say it's uncertain, it's risky. And we don't even know when new prices will arrive. So just as a benchmark, for half an hour, Apple stock prices have the examples that I use. This changes over time, right? But roughly you can think of it like 40,000, 50,000, 30,000 ticks, right? You can observe for half an hour, or in other words, like 40 to 60,000, for example, or even 100,000 per hour. But it's arriving in a random fashion, not in homogeneous intervals. Therefore, I want to put this here to sleep in a random fashion, random. Now I go with the uniformly distributed values, but I put this times 2. So that executing it now will give us new values at random points in time. So will give us random values at random points in time. And this is, it's not exactly reality, because in reality there are price setting mechanisms, but the behavior, it's pretty close to what we now see. We don't know the price in advance, and we don't even know when the next price will arrive. So that's what we see here. Yeah, somebody asking, instead of the 127 to set the local host, I would go with the 127, because from my experience, this is what works throughout the operating system landscape. So this works on Windows, this works on Mac and Linux. So I could use here, for example, the quadruple zeros, but on Windows, I think it's still required. I'm not sure about that, the 127 for the local host. And local host, depending on the browser, maybe, but here we are not in the browser. We are here in the Python world. So depending on where and what you do, this might be a little bit different. So I would recommend to follow it in the way I'm doing it. So we now see also that we have a ton of digits here. This might also not be realistic, because prices, stock prices, are not quoted with that many digits, right? So I could go here and, for example, do a rounding of that value. For example, when I do print here, like sorry, I was overriding this here, like round. I can do that later on as well, round, but not completely, like maybe 3 digits would do the trick. So this is cosmetics. We want to also, or not only print this out, I have set up my socket infrastructure, but I'm not using it yet, right? So in that sense, I now change the approach slightly. I generate a message here, and the message is as follows. I say for Apple stock price, I send here the new updated stock price. This is an F string, and instead of just printing the price here, I now go with the message, and I don't need this anymore here, right? The message, but just to stick to the 3 digits, I can do the formatting here. So what has changed now? Still not communicating with the server, but we now get here also 3 digits, and instead of just the number, we get Apple. So it indicates that we are dealing here with Apple stock price, and that's the simulated stock price. And you see, this works 24/7, no matter whether markets are open or not. This is now our little sandbox. Again, instead of just printing it, I would like to send this socket send string message via the socket. When I execute this now, we don't see anything, but we would assume, if everything is correctly set up, that via the socket that we have opened, the message is sent. But since we don't have yet a receiver, like a subscriber to our publisher, we cannot be sure what is happening there. So that's the next step, right? We are there, that's fine, okay. Now the next step. I open a new tab with the tick client py. So simple tick data client. I work again with set and queue, obviously, so it needs to fit somehow. The context object is the base one, stays the same. Context. The socket now is different. Context.socket. Now it's setmq subscriber. This is just one character, right? Here it is setmq sub for subscriber. Here we have setmq pub for publisher. So socket on that side is now connect instead of bind. Connect TCP 127.001.555. This now should be in line. This is like, think of it like a radio frequency, right? When you want to listen to a radio program, at least back in the old days, AM, FM, you need to fine tune your radio in order to be on the correct frequency. If you are on a different frequency, even slightly different, 5556, you won't hear anything, right? And then we have here a socket set sock opt string. Set MQ. This is now a further customization for the subscriber. Subscribe, that's a formal aspect now. I subscribe to everything on the channel, if you like. Here, I don't need to do any calculations, right? I'm like the passive part in this relationship, in the sense of the server is sending data and the client is retrieving the data. The client doesn't simulate anything, doesn't do anything at random points in time. Now we are the consumer, if you like, but the consumer should do this also for a longer while. So while true, right? I do now the following message. Now socket receive string and message, not message, nothing like this. And when I want to look at it, I print it out. So now I have no server running, meaning that when I execute this script, you don't see anything happening. Again, there is no tick server running. This is like tuning in to a radio frequency and there is no program going on, then you won't hear anything. Therefore, I now open a new instance here and execute my tick server and let it run. We know if we don't stop it, it will run forever. And when I now go up to my tick client and execute the script again, you see that the script now, since the server is sending data, is retrieving the data, at least the message. Speaking of data, yeah, in general terms, it's receiving the string here as a message, right? AAPL 103 point something, that's the current data point. So we have now a working socket communication. The server is sending as long as we let it, and the client, as long as we run it, will be retrieving the data. But the two of them don't do that much more. We have the tick client retrieving the data tick by tick, and yeah, it is, what shall I say? It's just printing it out and it forgets the previous message immediately. So we have no mechanism yet implemented with regards to collecting the data. So, right. Let me therefore do the following. So, copy tick client to tick collector.py and type e tick collector. So let me just give it a batch. That's the editor, right? That's the tick server, right? And when I'm down here, I can, for example, now get a tick client running here. Python tick client, all right? So that's running, and I can have more tick clients. Just to have this point made clear, like in the real world, there might be only one tick data server that you want to work with, but there are probably more than you that are listening to the real-time data, right? When you think again in terms of NASDAQ spitting out data directly or via Bloomberg, via Refinitiv, for example, or Jones, then there are maybe thousands of people listening at the same time to the same tick server, right? If there is a new price point for an Apple stock price, it's not only one person or not only one institution who is interested in the new data, it's probably quite a few of them, right? So having made this important point here, I now want to do a collection. So here, let me change the tick data collector. Tick data collector. In a very simple case, we could say raw, for example, is a list object, and whenever we retrieve some data, I simply append the message. I simply append the message to the list object, not list. I've said this works from the outside as before, but in the backend it should now collect the data. When I stop this process, I don't have a chance to inspect the data, but I have another mechanism namely that I go down here and stop this and call this now tick collector. Not that I could have more of them, but just to save a bit of real estate. Now tick collector. So you see me on the left hand side typing the badges here. And I want to run this now from IPython on the shell here. And when I run this, run tick collector, and you will see in a minute why I'm doing this. So the printout will be the same. I wait a little bit so that we have quite a bit of data. Let me stop it now. When I stop it here from within IPython, my Python kernel is still alive. And I have my raw object now accessible. So it wasn't destroyed when I stopped the kernel like before. We have now all the data collected, like Apple 108, 588, Apple 109, etc. You see here the data. It's not yet, I would say, in a wonderful manner here, but it is a collection of the data, right? We can improve probably a little bit here and can, for example, say something like this, that I say I have the symbol and the price via the message and do a split. You might recall a split that we have done. Split by default works on the blank. So now I have my message in two parts with the symbol and the price, and I can now, for example, collect tuples of symbol and the floating point version of price, because this will still be a string even after the split. The symbol is a string, that's fine. Right? There's no deal with having the symbol as a string. But here, if you want to do some calculation, some further processing or whatnot, this is probably then better as a float instead of a string object. So let me rerun this. So run tick collector here, IPython, do the collection. Sometimes it goes faster randomly, sometimes slower, or it's done randomly here. Right. Okay, should be good. I don't know how many we've got. And we have here now raw as before. When I open this, you see we now have tuples where the first element is a string in the form of a symbol, and the second element here now is a floating point value. Right? So this might now be interesting or not already. I think to master the basics of socket communication is, like I said, with regard to Docker and cloud, it's a real skill. And I want to now get a little bit more elaborate with regard to what we do here. Meaning that I go back and adjust the server. But before I do that, I might push this to the gist, but I need to probably do an update here to include the Python files as well. Batch update. In the gist, they usually then appear at the very end. Here we go. In the gist, you now find the tick client, collector. This is now sorted alphabetically. We started with the tick server, then did the tick client, the very simple one, then the tick collector. Right? So I now want to go and adjust the tick data server to be a bit more realistic. Right? So how do we do that? How do we go about this? At least you have now the standard case covered. Yep. Opening this here and getting back to the editor. The first thing that I want to do is I want to improve the tick server to include a second instrument, like Microsoft, sticking to our data. Microsoft also starting at 100. So now, since we are dealing with two, I want to differentiate two cases. So if random, so I entered the cases are differentiated by drawing a random number. If my uniformly distributed random number is greater than 0.5, then I want to go with Apple. Here, right? In the other case, else I want to go with Microsoft. Random Gauss 0, 1 over 2. The message then would be F Microsoft, MSFT, and we also report just 3 digits. We don't need like 10 digits for our little use case here. And I can, this is better moved 1, 2, 3 over here, because the message just won't. So I don't need to repeat this every time. I send the message, I print the message, then I sleep. I have the same volatility assumed, but now I have two. In the one case, we get Apple, in the other case, Microsoft, and it's 50-50. We could, for example, say I want to have, let's say, Apple more frequently updated, right? Maybe I go with 0.45 so that we have here not a 50-50. I could also go and say here something like Microsoft has a lower volatility, like dividing by 0.2, but in the end it will remain simulation. Right? So when I need to save this now, save this. I need to stop the tick server, and rerun it. And we now get, as you can see, we get sometimes Microsoft, sometimes Apple. You see here 3 Microsoft quotes in a row, Apple, Microsoft, Apple. Right? This is just like to have something that might remotely resemble the reality. On the right-hand side, with regard to the tick client, you see, I didn't need to change anything since I subscribed to the everything that is coming via the channel. I get every message that's coming via the socket. In this context now, I can show you what this configuration here does. Namely, here I was saying it subscribes to everything, to all the messages, right? And I can now, for example, now it makes sense if you like, I can say I'm just interested in Microsoft, right? So when I now go down here and do another Python tick client with a new code, this will still run as it was running. So everything that is running is unaffected by my source code change here. So this is unaffected, but the new one that I'm starting here, it's only retrieving, as you can see, it's only retrieving the Microsoft one. So in that sense, the subscribe option here, ZMQ subscribe, allows me to filter messages. And you can think of a use case in the real world. Of course, I mean, if you're subscribing to a streaming service where you get for the 500 names in the S&P 500 real-time data, you probably don't want to retrieve all the 500 at the same time. You say, well, I'm interested in just one, or I'm interested in 10 or 20 or 50, right? And here we have now a simple case where I said, well, the one client with the original source code, it's just retrieving or is retrieving everything, and the new one where I've set here the subscribe option to Microsoft only, it's only retrieving the Microsoft quotes. Right? When I now run the tick collector again, the tick collector is configured as before, retrieving all the data, right? Not just a selection of one of the two. Right? So when I stop this, have a look at raw, we now have obviously data for Apple as well as for Microsoft here in the tuple form, which is a little bit better, yeah, because we are having the quotes now in yeah, floating point format and not in just a string format with which we could hardly calculate. But it's still, this is just yeah, this is my backpack analogy. We are collecting tick by tick here and putting it into a list object, which for sure is not the most convenient form for us to do calculations. Therefore, for sure, one of the major benefits that we have is that we have learned about NumPy and Pandas in particular, and the goal would be to put all of this, what we have here, with enriched data, augmented data, for example, in the form of time information, into a Dataframe object, so that we can do quite a bit more with it. But that's the starting point, right? So we are moving here step by step. So that's the simple tick, here the tick collector, right? Subscribing to everything there, right? So let me now copy the tick collector and come up with a solution that might be a bit better, nicer, right? Namely using Pandas to this end. So copying tick collector, so tick data frame, I call this tick data frame. Let me open this tick data frame. Exactly the same code, since it's just a copy. So here, data collector using Pandas data frame objects. My goodness, I'm obviously not sitting right in front of my keyboard, like one keystroke off. Speaking of using Pandas data frames, we probably need Pandas, right? Import Pandas as PD. It's not a big surprise. And here I would go with, I would simply call this now data, PD data frame. Empty data frame. This works like an empty list object. An empty tuple doesn't really make sense, but an empty list object where we put data in, or data frame where we put additional data in, this works, right? So now instead of the append, we will have append there as well, But after we have done that trick, I do the following. So df will be a data frame object, PD data frame. And now I use a dictionary approach, and I say symbol, symbol, symbol is symbol, and price here is the floating point version of price. Index I set simply to 0. And then I do here data as PD concat. I concatenate now data frame objects. Here the data frame object from before and my df, and ignore, this is now a little bit technical, index true. That's not needed anymore. So I don't know if this is all correct. Sometimes now after a few hours you see me here on my classes, so I'm really doing my best, and I notice when I don't use the classes after a little while my eyesight becomes better with like training, like weightlifting. Let me see if the code per se is working. It seems to work, and at least it doesn't give me any kind of error. Right. So same as with the other approach, with the first version of the tick data collector, I now need IPython in order to be able to inspect what I have collected. Right. So here IPython run tick data frame. I mean, another approach would be to collect something, to write it on disk, and to inspect it there. But I feel that here the IPython approach, where the kernel is still alive and I have access to my objects from the run, from the execution, is the more efficient one. So stopping it, cleaning up, now I have the data object, right? Where I have a column where the symbol is to be found, and I have the price column where the prices are to be found. You see here in the meantime, Apple by chance is outperforming Microsoft in my case. This could of course go completely differently. Every once in a while when I do these demonstrations or trainings, people are asking, where's this data from? And I need to reiterate and re-emphasize that this data is just simulated data. There is no real data source behind it, nor does it signal any kind of future development. This is just random data here that we simulate, right? So we have now a data frame, and we could do things like data here, and now something like data symbol here for the symbol column is equals, let's say, MSFT, for example, and we can select only those values, right, that are relevant for Microsoft. The same can be done. This is, of course, a complete analogy with the Apple stock price, where I have now another data frame, which is just about the Apple stock price, and Microsoft is blended out. Of course, you see here the index values are now not like a typical range index. We have, of course, now just a selection of the relevant prices. I just wanted to indicate that here the mix up of the values is not a big deal for what we are doing here, right? All right, this looks good. We have it now in a data frame. What, of course, is missing throughout of everything that I have been doing now is any time component. With our data set, the CSV file, FinData CSV, we've had date information, so 20 21, for example, 2nd of April, let's say. I don't know if this was a trading day. Here we are having just prices and symbols, but no information. With regards to real-time, to tick data, we obviously are not dealing only with the days, but we need an exact timestamp. And this is something that I want to add now to the logic here. And to this end, I need the datetime module, which we have used already a few times. Import datetime. No, maybe I would have better moved it up there. I'm a big fan, I don't know why, with my editors at O'Reilly, they always, yeah, there are certain, I'm a big fan of PEP 8, but I'm also a big fan of importing in a visually appealing manner. So here you see, I like to have like the shortest packages first, so that we have something like a triangle, but this is, everybody has their spleen, right? So now that I have imported datetime, I can do a timestamping. Here I retrieve a message, and immediately after the retrieval of the message, I want to collect a timestamp. So datetime now. Now I know exactly when the message was retrieved. The retrieval was at a random time, so I couldn't foresee it, I couldn't forecast the arrival time, but at least once I have retrieved it, I can timestamp it, which is done in practice as well, right? But in practice, not going into all the details, you might be aware of that whenever you retrieve something from a server, from your broker, your trading platform, your data provider, it has a timestamp already. I have simply skipped that part with regard to my tick data server. So now we have here symbol price, and we have on top of that, we have the timestamp, and I'm going to use the timestamp now here as the index T. And then I say here, not ignore index true anymore, but rather it should use the index, because we now have a proper index. Let me save this now, and let me go down here, rerun my little example, run tick data frame. As usual, we let it collect a few elements, a few data points. Okay, should be good. And now in data, I have a proper datetime index. Wonderful, right? We have timestamps down here to the second, millisecond, microsecond level with the symbol and the quote. And of course, like before, I can do the selection according to the symbols. If I'm only interested in the Apple stock price, for example, and if I just want to do some trading or analysis based on the Apple stock price here. So this works out of the box, right? Pretty convenient, and we know now if we were within a Jupyter Notebook context, I could do some visualization. I can even do a visualization here. I can show you this afterwards as well, when we might have collected a few more. So that's now the tick server spitting out data for 2 symbols. This could be 30 symbols, 40, 500, whatever. We focus on 2. We could, if we like, subscribe to just 1. I've shown this. Or we simply collect everything that we get in a single data frame and then do the selection afterwards. That's often a pretty efficient approach, as you can see here, right? So that's now, I think, a good point where we have arrived. If we haven't done so yet, right? But just that we have seen that as well, and I've mentioned this before. If you have collected that data and say, yeah, I want to work with that data later on, I can like write this here also to CSV as one example, right? Like tick data CSV, let's say, I can write this to disk. And now let me get back to my Jupyter Lab. Here, there are the files and tick data CSV. This is now stored here. And of course, it's a pretty small data set, right? Which has a couple of entries only with our date column here, the symbol column, and the price column. So just in case you want to persist your data as they say, right? So one more element that I want to add to the story. Collecting tick data is, how shall I say, it's an important task, obviously. I mean, collection implies retrieval and then collection. And the next question is, what do we do with the tick data? One of the typical things that we do is that we put the tick data that we retrieve into homogeneous time intervals, meaning hardly ever in trading you will work with tick data directly. If you're not a market maker or high frequency trader, if you're a regular algorithmic trader, let's say, whatever this means, I have my idea of that, I hope you do. You probably want to resample the data, for example, and I stick here to the second level, to 5-second bars. So let me show you what I mean. We have here tick data, but, and I go now with AAPL, that's something else here, and I take just from data symbol, maybe we don't have that many here, AAPL. So now I have just my AAPL data. I have a few tick data points, that's fine. What I want to do now is I want to do a resampling to 5 seconds. AAPL, resample, you see it down here, resample, right? Resample. When I simply do it like this, it says missing one required argument. What is the rule, right? Yeah, the rule is that I go with the last value, right? Invalid frequency. Oh, sorry. I was wrong. Last is required, but here I was talking about 5 seconds, so I had a mental check behind it. And here I then need to specify 4 to 5 seconds what to use. It's the last value. So you see now a homogeneous time grid. We are not on the millisecond, microsecond level anymore. We are now on the 5-second bar level. But when I show you the whole data set again, let us check. We have here 15, and that's kind of interesting how 15, that's the price of here, but this is 16. So 31 minutes, 16 seconds. And we see at 15 now the price from 16. So this cannot be correct, because at 4 p.m., 31 minutes and 15 seconds, we couldn't have known the price which was retrieved at 1 second or 2 seconds later. So there is something missing, and that's a very important point when you do such exercises here. We need, at least in finance, maybe in other domains, I don't know, I cannot name an example, but here we need to set the label to the right-hand side. And with the right-hand side, it now includes everything up until 20 seconds. And you see this is now the correct one, because at 20 seconds, that price was known. And 25, we have here 23, right? That was known as well, etc. pp. So that's also an important task, that you say, well, my strategy is not based on tick data, but I collect the tick data, and my trading strategy yeah, here my simple example, because I don't have that much data, my strategy, that's the assumption, I was based on 5-second bars. And here you see how you can resample the 5-second bars, right? Or the tick data to 5-second bars, with the important option here of label right, so that we are not introducing any kind of foresight bias into our analysis, into our story, right? From that point on, once you have that data in homogeneous form, you would then implement your training logic. For example, we have had the binary classification. This could now be applied to the data that we have available, and then we in real time, which technically speaking is then an online algorithm, has nothing to do with the web and being online. This is a computer science term. You would generate signals, you would implement the signals and then follow along, maybe stop loss orders or whatever. And so you would be in the game. Something that we also cover in a ton of detail with everything around with regard to logging, monitoring, deploying in the cloud, etc. And doing the whole exercise with real APIs, for example, from Wanda or a UK broker or European broker. Yeah, but that's obviously, I mean, pretty sure everybody gets the gist here. It's a pretty important task in algorithmic trading, in trading in general, and in real-time market analysis, whatever the analysis is used for. It can be risk management, trading, investment management, whatever the use case is. Yeah, I think that's a good point. So we have now also seen that we can use beneficially and also easily, efficiently, I would say, Pandas Dataframe objects to collect real-time data, not just to efficiently retrieve a static historical data from a remote server, but also here in real-time and grow our database and what we want to use in such a context later on in an efficient manner. We can write it on this, we can use it, we can trade. The sky is the limit, and your imagination basically here is indeed the limit for you, what you can do with it. The tools are there, they are there for free, and I hope you have seen that the combination of the few ones, only the few ones that we have covered in the bootcamp is already a pretty powerful combination. Yeah, that was roughly what I wanted to achieve for today. Of course, let me just check for a second. I will also stop all my the executions here are independent of you, but sometimes I have these processes running for days and sometimes even weeks on end. If I miss to stop them, I have saved here everything. I need to just update the gist with the latest additions. Here, the tick data frame 1, right? You go here, you see it, simple tick data collector using Pandas data frame objects. You see that the code is not that much, and you have afterwards now, let's say maybe your other 50 lines of code which implement the logic and the trading stuff, including or excluding resampling, trading logic, prediction, machine learning, technical indicators, and whatnot. At least you have now all the resources from what we have been doing together in a single place. The videos and the recordings are available on our Quant platform. They're also uploaded to our YouTube channel. And before we close up and wrap up today's session, I want to reiterate, if you like what we have been doing over the course of the bootcamp, you have the chance to sign up at the super early bird rate over the next 48 hours. On Monday at 2 p.m. CEST, we are going to start with the May cohort of our certificate program, where you have more than 250 hours of instruction and 2,500 pages of resources and tons of code that come in a single comprehensive and coherent package. If you have questions, you have our contact information. You can use the Discord server, email, whatever you like. In that sense, I hope you've had as much fun and excitement as I had for our online bootcamp. Hope to see you maybe in the next one. I was thinking of doing maybe a more advanced one where we would add on top of what we have been doing here in the near future. Let me know your thoughts. Let me know what you've been missing. Let me know what you've liked about it, and also let me know maybe what you will be interested in learning about in a similar format as the one here. In any case, I wish you happy Python coding. All the best. See you hopefully soon. Take care. Bye bye.